These are the notes for Module J, Unit 1, Lesson 2. The topic is properties of waves. The essential question says, how can we describe a wave? The explanation says, by the end of this lesson, you should be able to identify characteristics of a wave and describe wave behavior. You have 3 learning targets in this lesson. The first is, I can label parts of a wave and use correct vocabulary to describe it. The second learning target is, I can explain what affects the energy of a wave and why waves lose energy over time. And the third learning target is, I can explain what determines the speed of a wave. Just like in lesson 1, the vocabulary for this lesson is embedded in the notes. So you don't have vocabulary words listed in your notes, and you don't need to do any separate definitions. We'll go through all of those as we go through the notes. The first term in this lesson is wavelength. The wavelength is the length of one complete wave cycle. So wavelength is measured from a point on one wave to an identical point on the very next wave. You can measure from crest to crest or trough to trough on a transverse wave, or you can measure from the start of one rarefaction to the start of the next, or the start of one compression to the start of the next compression on a longitudinal wave. Wavelength is important because it tells us about the energy of a wave. The longer the wavelength, the farther apart the waves are, the less energy the wave has. The second term in the notes is amplitude. Amplitude is defined as the maximum distance a wave vibrates from rest position. If you picture the way a lake looks on a day that it's perfectly calm, there are no waves, and the surface of the lake looks like glass, that's the rest position. That's where the water would be if there were no waves on the lake. So a rest position is the position where the matter would be if there were not any waves traveling through it. And amplitude measures how high above that position the wave is causing the matter to vibrate. So you measure amplitude from either the bottom of the trough or the top of the crest to the rest position. And whether you measure from crest to rest position or trough to rest position, you'll get the same measurement. The bigger the amplitude of the wave, the more energy the wave has. And when we talk about sound, waves that have bigger amplitude are louder. Waves that have smaller amplitude and less energy are softer sounds. The next term in the notes is frequency. Frequency is the number of waves produced in a given time. The frequency something happens is how often it happens. So the frequency of a wave is how many waves are produced in, typically we measure in 1 second. The unit of measurement for frequency is the hertz, which is abbreviated Hz, and 1 hertz is equal to 1 wave per second. This is a term you maybe have heard with radio stations. Each radio station has a unique frequency, like 97.1 or 101.3. It's a measure of the number of waves produced per second for the signal of that radio station. The period of a wave, it has to do with time. Period is the time it takes for one wavelength to pass by a point. Because period is a time measurement, it's measured in seconds. Waves that have a shorter period are shorter, faster waves. Wave speed is the distance a wave travels per second. You have learned how to measure speed. Speed is equal to distance divided by time, and we can find that same calculation for a wave. If we measure how far it travels and how long it takes the wave to travel that distance, we can calculate its speed. The interesting thing about wave speed is that waves travel faster through more dense materials. That means a wave will travel faster through a solid than it would through a liquid or a gas. The reason for that is that those solid materials, those denser materials, have particles that are closer together, so they very quickly bump into each other and pass off the wave vibrations. Particles in something like a gas, while they're moving quickly, are really spread out, and so they don't collide and pass off the wave vibrations as often. The last term in the notes today is the wavefront. One wavefront is all of the points covered by a wave at a certain point in time. So I have a picture of ripples on a pond here, and there is a really nice explanation of this in an illustration in the digital lesson if you'd like to see a video with movement. Each of these ripples on this wave count as one wavefront. So here, one ripple is one wavefront. Here's another one. And with these ripples, with these wavefronts, The ripple that's closest to where the droplet hits or closest to the source of the sound is going to have the most energy because it covers the smallest area. As that ripple, that wave spreads out over time, it's still got the same amount of energy, but it's spread over a greater and greater area. So any spot on that ripple would have less energy than a spot on the wavefront that's closer to the source of the wave. I like to think about this the way I put frosting on a cake. When I'm frosting a cake, I dump a big glob of frosting right on the center of the cake. So that first spot where the frosting hits initially has maybe 3 inches of frosting on it. And then as I frost the cake, I use my spatula and I spread the frosting out so it smoothly covers the entire cake. It's just like the wavefront spreading. So my cake still has the same amount of frosting overall, but once I've spread the frosting out, each individual piece of cake maybe has a 1/4 inch of frosting instead of that big 3-inch thick dollop. So the wavefront, each wavefront has the same amount of energy the whole time, but as the wavefront spreads out, it's the same amount of energy spread over a greater and greater area. And so with these ripples, as they spread farther and farther away, and the energy is spread over a greater and greater area, they appear to disappear. We know that's not true because the law of conservation of energy tells us that energy isn't created or destroyed. But eventually the ripple spreads out enough that there's so little energy that we can't detect it. The last thing in your notes is a diagram. I put the picture in your notes, and the best way for you to do this is just like it says here, copy and paste this image. So copy is Control-C, paste is Control-V. Move the image from your notes into a drawing. So do Insert, Drawing, and then paste this into the drawing, and then you can add text boxes and type the labels. We need to label some parts of this wave. So first of all, we're going to label some things that we've talked about in class but aren't actually given on this diagram. The crest is the highest part of the wave. The trough is the lowest part of a transverse wave. And remember, with a transverse wave, we've got a wave that's causing the material to vibrate perpendicular to the direction the wave is traveling. Amplitude, we learned today, is a measure of the distance from rest position. Let's add that label, this yellow line in the middle, to the top of the crest or to the bottom of the trough. And rest position here is this yellow line through the center. That's where the material would be if there were not waves passing through it. Wavelength, right here, is the distance from a spot on one wave to an identical spot on the next wave. So here they measured from trough to trough. And then frequency is the number of waves in a given amount of time. So this is measuring in 1 second. We had, it looks like, about 2.5 waves. So that would be the frequency. So add all of those labels to the diagram in your notes. One of your learning targets is being able to label these things on a diagram, so you can expect to see that on the Module J test. And these are the notes for Module J, Unit 1, Lesson 2.